Okay, we're gonna get started. Thank you for coming, first of all. This is a lot of people, so I'm kind of nervous. My name is Mate. Nice to meet you. Hopefully we'll get to chat after the presentation. Feel free to grab me. I love talking about Rust, VR, 3D engines, all sorts of stuff. Can you all hear me, by the way? Yeah. Is this loud enough? Okay, cool. Let's see what else. We have a couple of administrivia. So yeah, my name is Mate. Feel free to add me on LinkedIn. If you want to contact me, you can message me on meetup.com. And special thanks to Braid, where I work, for helping me organize this meetup. Thank you for coming. And also, please welcome Paul Masurel, who's going to tell us about his work on Quickwit and Tantivy, and who actually used to run, among other people, this Tokyo Rust meetup, right?
Yeah, I wasn't that involved actually, but yes, I think I'm listed
Okay,
with
well,
the
it said on meetup.com that you were one of the organizers, yeah. So this is formally passing the torch.
Hello, everyone. Thank you for coming. My name is Paul Masurel. I usually go by the handle name Filmicoton on GitHub, Twitter, and usual social networks. I'm the CEO of Quickwit. Yeah, I'm going to try this. I think it's going to be a very lonely experience, but how many people have heard of Quickwit? Two, not too bad. What about Tantivy? 3, 4, okay. So not so much. Hopefully at the end of the presentation you will be able to know a little bit more about those two projects. So Quickwit is a search engine company. We are building a distributed search engine. You can think of it as a fresh alternative to something like Elasticsearch if you are trying to index logs. So we are specialized on append-only data. We are very bad if you are trying to modify your data set a lot. We cannot back, for instance, e-commerce website or something like that. We are more on the other end of the spectrum of search engines. We are more into making it possible for you to index terabytes, hundreds of terabytes, petabytes of logs, and still be able to search it relatively fast. And most importantly, on the cheap. We are way cheaper than other solutions. That's what we do. So yeah, we love open source, and we love open source stuff as well. So we are entirely built in Rust. And I didn't list all of the crates that we use because there's too many of them. But I listed some of the crates that we contributed. So Quickwit is not a library. It's our project, a distributed search engine, it's entirely open source. And then there is Tantivy, which is it's a search engine library that is a little bit famous in the Rust world and also in the search world. It's an equivalent of Lucene, if you are familiar with Lucene from the Java world. And then, yeah, we also have contributed the Levenstein Automata crate, which is a crate with Levenstein Automata, if you are into that kind of things. ChitChat is a library to make it possible to do cluster formation. So you have a bunch of machines and you want to be able to have them know about each other and maybe share some small states. You can use ChitChat for that, and it will detect, for instance, if one machine dies and needs to leave the cluster. It's done through gossiping. The bitpacking crate is about integer compression, very efficient one. We'll talk a little bit about that in the presentation. And the search benchmark, the game, so the project. That's our project. Be nice, and at the end of the presentation, click the star button. We love stars. We collect them like Pokemon. Yeah. So the search benchmark the game. It looks like this. And it's kind of a differential benchmark testing different search engine. If you have your own search engine, you can add it to the benchmark relatively easily. It's not specific to Rust. So you have Lucene in there. Believe is written in Golang. Lucene is written in Rust, the one on the right here. And what's interesting in this benchmark is that you can choose different kind of queries. For instance, here we are just trying to fetch the 10 best documents, but you can pick like 10 best, but also you want to count the documents, which is very different because it means that you need to go through the entire doc set and just count the documents. And usually Tantivy is doing really well. So if you play with it, you will see that actually Pisa is faster. Pisa is a C++ project run by academics, and it's the fastest search engine that I know of. Yeah, and apart from that, Tantivy is the fastest that I know of. Yeah, so one question that I usually get when I talk about Tantivy is people ask me what makes it fast. And usually I think they have some kind of agenda, like they want me to say that it's thanks to Rust and that Java sucks. And it's actually more complicated than this, and the goal of this presentation is to explain a little bit about what makes Tantivy fast, because usually I only have 5 minutes to answer this question, and that's more a 40 minutes question. Yeah. Yeah, so we are gonna just discuss a little bit about what Tantivy is, and then discuss what makes Tantivy fast, and then I will talk a little bit about what Quickwit is and what makes it cost efficient. And feel free to interrupt me if you have questions in the middle. If you just want to say this is wrong, please do so. That's perfectly fine. We are small enough communities that we can do that kind of stuff. Okay, so Tantivy, it's a library, so you cannot use it as a standalone program. It's something that you add to your program because you are building a search engine or you are building some kind of OLAP engine or whatnot. And usually your program looks like this. So you define your schema first. So here I just have one field and it's text. And then you have to index your documents. So the important piece here is that it's done in batch. So usually you will want to append as many documents as you want to the index and then call commit to get an important throughput, indexing throughput. And you can, to give you an idea, so Tantivy is very fast at indexing. It's way faster than all of the engines that we've seen in the list before. And I think the second one would be Lucene, and I think Tantivy is often like 3 times faster than Lucene at indexing. Yeah, to give you an idea, indexing the English Wikipedia, so it's about 8 gigabytes of data. It takes 4 minutes and a half on my laptop. So yeah, you can index volumes of data with Tantivy very nicely. So on the search side, it will look like this. You have to open your index, so you pass it a directory, and then you write your query and you search. So yeah, here I think the interesting thing is that we pass the query, and then we pass a so-called collector that defines what we want to do with the search results. So it's possible to say that you are interested into aggregating some statistics, or maybe you are just interested in the search results, or maybe you want some count. I don't know. And you can plug your own implementation of a collector in there. So it's possible to extend the library very easy. So what makes it fast? So first, it's not just a matter of rewriting stuff in Rust. So Lucene, like Lucene with an R, is a project from a Chinese company. They just rewrote Lucene in Rust. And they ended up with a solution that is actually slower than Lucene all over the board. So, and it's not the first time actually. There was also an effort called C Lucene. That was a re-implementation in C, and it was also slower than Lucene. So you cannot just like take the code base and do a translation and everything will be fast. Things just do not work that way. You have to write actual Rust code to get performance, and then if you want great performance, you will have to sweat a little bit. So yeah, I have trouble answering this question in 5 minutes, so it's going to take a little bit of time because it's not one silver bullet, it's actually a bunch of lead bullets, and I try to list all of them. So yeah, of course, algorithm and data structures. That one is usually when I write something in Tantivy, my default is to copy what is done in Lucene. So most of the algorithms are actually the same as in Lucene. It's not true everywhere, but almost everywhere. So that's not really what makes, for most of the search benchmarks, it's not what makes us faster. The index format, it's close to Lucene, but we will see that it differs in some way. So there is one point which is, it's generally speaking, if you write a search engine in Java, you will have a very hard time because Java will force you to, for instance, box your integers or stuff like that when you work with collections. So you will have basically to rewrite every single collections, and that's what Lucene does. In Rust, I'm able to pull stuff from the standard library. Usually you get a best-in-class implementation and it's fast out of the box. So here it's like just a straight win from Rust, and it's amazing. And so one point that I rarely hear about is Rust is optimization friendly. So what's magical with a language like Rust or C or C++ is that you can write your code. Maybe it's not as fast as Java, but you can, or maybe it's just as fast as Java and it's not faster, but you can then look for the hot piece of code that you have and you can focus on it. Maybe it's just 10 lines of code, and you can go way above the performance that you were getting from Java because you have all of the tools that you want to do it. So we will discuss about that. One very important part also in my job is Rust makes it very simple to make a difference between static dispatch and dynamic dispatch. We'll talk a little bit about that too. And then we have access to SIMD instructions. And so the order here is not entirely random, so I tend to talk on the internet a little bit too much about SIMD instructions, so people believe that our source code is plagued with SIMD instructions. That's not true at all. We have just a few lines of SIMD instructions sprinkled over the code base, but they are very important. And after writing this list, I'm not cheating there. After writing this list, I noticed that there was one very tiny example where I was actually covering every single one of these points all at once, except the one about the less hoops to jump into, blah, 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 to get the right thing. And it's intersections. So once, and I'm going to simplify stuff, and I will consider just running a query over the intersection of two terms, hello and world. So it seems like a very simple problem. I suspect that a lot of you already know what an inverted index is, but I will still explain a little bit how it works. So in Tantivy, when you add a document, it gets a document ID. Document ID is an unsigned 32-bit integer, and it's just auto-incremented. The first document gets doc ID 0, the second one gets doc ID 1. It's as simple as this. And an inverted index is just like a map from terms, so here, hello and world, to a so-called posting list, and a posting list is just a sorted list of doc IDs. It's as simple as this. And so now we have two questions. We're not going to discuss about the term dictionary part. So we are not going to discuss about how the terms are sorted and how we associate the terms to the posting list. So we will focus on how we lay out on the disk the posting list, so the list of doc IDs containing hello and containing world, and how we compute the intersection of these two posting lists. So it sounds like a very simple problem. We could probably wrap it up in 30 minutes if it was a programming interview, but you will see that it's actually much deeper than what you might expect. So first, how do we compress? How do we lay out the data on the disk? So we want to compress stuff, and we use a first trick that is very common in search engine. We do delta compression. So I said that the doc IDs were sorted in the list. So instead of storing the doc ID directly, we store the difference between two consecutive doc IDs. Very simple trick. The point there is that we get integers that are smaller, and every single integer compression methods that you might know of are relying on the idea that the integers are rather small, and so you don't have to burn 32 bits to store them. And then on top of doing that, we use a compression that is relatively simple, that is called bit packing. The idea is you group your doc IDs by blocks of 128 integers, and you notice that the largest one might be, I don't know, 15. If it's 15, then you know that you can represent every single one of these integers of 4 bits. So you store this metadata about the block. You just store the fact that this block is encoded over 4 bits, and you only use 4 bits per integer. Very, very simple. But then, so there is a trick that I didn't detail here to write the integer on the disk in such an order that it makes it very easy to do this bit packing and this bit unpacking and this delta integration, so the operation of getting the doc IDs from the delta encoded docs. There is a way to do that with SIMD instructions. I didn't invent it. It's a method that was published by Daniel Lemire, which is very famous in the very small domain of integer compression. And yeah, so this method makes it possible to decompress 6.5 billions to 9 billions integers per second. So in this kind of work, it's very important to keep an idea of what are the order of magnitudes that you should expect. 9 billions of integers per second, it's a laptop. The frequency of my CPU, it varies between 1.6 and it can spike at 3 gigahertz or something like that. So yeah, it's extremely fast. And also in terms of memory, we are flirting with the bandwidth of memory if it was uncompressed. So I'm using DDR3 here. The bandwidth is, no, it's DDR4, but if it was DDR3, for instance, the bandwidth is 12 gigabytes per second. And yeah, we are, if it was like 4 bytes per integers, we are already above this, so it's quite neat. So yeah, if you are interested in this, you can, so the bit packing crate implements all this, and it also implements the methods for different SIMD instruction sets. So here we are very conservative. We use SSE3 instructions. But if your CPU does not have this instruction set, we sniff it at runtime, and we have a different implementation for this CPU. And if it's at compile time, then the routine for SSE3, of course, will not be compiled at all. So I think it's interesting to know how that kind of stuff is done. And then there is also an implementation that was added recently for ARM. So yeah. So now with this we have an iterator of blocks of doc IDs. So it's one block is 128 doc IDs. So we could build very easily an iterator over doc IDs. Like flat map, right? And treat that as, let's compute the intersection of two sorted iterators. That's like a super common interview question, right? So yeah, I wrote like the typical answer for this. I think it's called like merging or zipping two iterators. Yeah, I wrote the right version because it's much simpler than like introducing like pickable iterators and doing weird stuff like that, but you get the idea. Because the integers are, the iterators are sorted, you just identify which iterator is, actually I wrote the union here, I made a mistake. So there is no push here and here. Sorry, I did that right before I did that today actually. But you get the idea. You advance the iterator that is lagging behind, and when the two iterators are on the same element, then you know that it's in the intersection and you can add it to the output. So the first version of Tantivy, we are doing this, and the search benchmark was already there. So we had a point of comparison with Lucene. And the search benchmark is great because it gives you results like that are not a very simple benchmark that would be an average over a set of queries. It gives you result per queries. And so Tantivy was doing extremely bad, like it was up to 6 times slower than Lucene on very specific queries. And I gave you an example here, which is the and Incredibles, so the intersection of the and Incredibles. And yeah, that's the interactive part of the presentation. Can you guys think what could be the reason why it's not very efficient to do this? People don't tell you that in interviews, right? It's a very bad way to do intersection over iterators sometimes.
Because it's all open.
Sorry?
Because it's all off and linear. The complexity is all off and.
Oh, yeah, often is not that bad, right?
Yeah, but it's this. You can just do bit masking.
You can just what?
Bit masking and bit comparing.
So it's bit masking is not happening there in Lucene or Tantivy, but yeah, you can do better here. So the trouble here is that it's a posting list that contains every single doc IDs in your dataset, basically. So dataset is Wikipedia, and you can expect that every single document will have the in it. Incredibles, not so much, and so you have a document frequency that is way larger here and not here. And so if you look at the algorithm that we had before, Tantivy and Lucene are using some kind of skip index to make it better. So the way we do this in Lucene, in Tantivy, is we have a companion index to this posting list that just stores for each block. It's a list, and you get for each block the last document in the block, and then the block offset. I'm lying a little bit, but that's it. And so when you are trying to seek for a document, so you know that your other leg is already at document 1000, you don't need to go +1, +1, +1. What you do is that you seek into this data structure, and you can go directly to the block that might actually contain your document. So it's much faster. And so I was a little bit... I knew about the problem, but I saw that block decompression was so fast that it wouldn't be a problem. But actually, it really showed up in the benchmark, so I had to implement that. So now our intersection looks a little bit more like this. So we have a docset trait, and we have a seek function that takes a target. So it's a target document. So like if you do your intersection, you're gonna call it with, like if you have two legs, two terms, two posting lists, and the first posting list is at document 23, you call the seek on the other leg, and you see if you went past this document, or if you actually reach the document, in which case that's your next document in the intersection. So nothing too complicated, I hope. Now we have another question. So we have an index to be able to identify what will be the right blocks, the blocks that might contain our document. How do we seek into this block? So we have a block of 128 documents, and we want to see what is the document that is right after the document that we are seeking. So we are trying to implement this function here. We did the part where we seek the block, and now we need to call seek into the right block. So possible version would be to do a binary search, and that makes absolute sense. Of course, here I didn't put an array that is sized to 128 because maybe we are in the middle of the block and it's actually smaller than, maybe the last document that we looked was, I don't know, at half of the block. So we can search into a smaller block. So that's a perfectly reasonable implementation. We can be a little bit more fancy and think, oh, it's a little bit too much to search into the entire block. We can start by an exponential search. That's a very common trick in that kind of search. We do an exponential search to find value that is past the document that we are searching, and then we follow by a binary search into this reduced array. That makes sense too, and at one point that was the implementation in Tantivy. What about this implementation? So if I'm asking, obviously it's the fastest implementation of the three. So it really looks like the binary search. Actually, I just re-implemented binary search, right? That's what it is. So it's just almost like the one that you have in the standard library. So one big difference here is first, I didn't try to be smart here and pass an array. I pass the entire block all of the time, which means that I know exactly what is the size of the array in the beginning, which means that Rust will be able to totally unroll the loop, which is a good news. And then the second thing is the way it's implemented makes it so that it's actually possible for the compiler to be branchless. So this code, you have an if statement here, but actually this code is transformed in such a way that it's actually doing start plus equal, and then the value that is obtained by a conditional move on pivots smaller than target. So if you look into, too bad. Yeah, I didn't have access to the internet. Yeah, if you look at the assembly code that is generated, so I'm sure you don't look at that necessarily every day, but the code is, there is no loop, so the first key takeaway, and there is no branch either, as you can see, and the branch was replaced by the cmove that you can see here. So if you plug that into, okay, I don't have the link, too bad. So if you're gonna have to believe me on that one, but if you plug that into a CPU simulator like UICA, it gives you a throughput of 9 cycles per iteration. So it's only 9 cycles to search into your 128 integer, which is really nice. So it was added last year, and it was, before the implementation was another implementer that I didn't show here that was using SIMD linear search, and we obtained a 10% speed improvement with this extremely simple implementation, so that was a very nice win. So Rust is low-level optimization friendly. It's very common for me to like copy-paste code in Godbolt or use cargo show ISM. So I don't know if you guys use cargo ISM. So there is a new project that gives a slightly nicer output called cargo show ISM. It's great. I recommend you to use it if you want to look into the assembly that Rust is generating. uica.uops.info is a website that gives you access to a tool where you can copy-paste assembly and see how it's actually executed on your CPU. It's a CPU simulator and gives you an idea of what is a bottleneck at a very low level and how much performance you should expect on your CPU. Of course you want to profile, but that's not specific to Rust. So I often use cargo flame graph because it's useful, and you can use perf. Hotspot is a GUI for profiling. Criterion is nice for macro benchmark. And yeah, the usual suspects in our case, it's often the inlining that is not happening. You thought it was happening, but it's not. Branchy code and location. Those will be, I guess, the most common usual suspects. You might have noticed when I showed the dogset implementation, the next in intersection, that I was showing this, and yeah, so I was passing a trait object, which means that so first the reason for why there is a trait here, even though I'm only talking about posting this, it's because we actually have other implementation of dogsets. So for instance, we have one dogset that is used for fuzzy term queries. So it's a dogset that shows you all of the documents that contain a term that is at Levenshtein distance 2 of another term, for instance. So we have different implementation of this dogset trait. And so a trait object, you might know that it's not great for performance. The reason for that is that most of the time you will end up with dynamic dispatch at runtime, and it's making the life of your compiler extremely hard when you use dynamic dispatch. So for instance, the compiler will not be able to do inlining, and it will not be able to do all kinds of optimization following inlining. So yeah, actually the code is a tiny bit more complicated. So we have an intersection struct that is implementing dogset, and this implementation struct uses generics to say, oh, okay, I know what is the type of the first and the second dogset that I'm trying to intersect, and then there is others dogset because it's actually in charge of doing the intersection of more than 2 dogsets. And then when we parse the query of a user and we convert it into a query, we actually do a little bit of inspection on the type of the dogset that we have. And if we see that we have for instance, the temp score, the temp score type for the dogset of the 2 first values, then we build a specialized intersection object. So you have code in the intersection.rs files, but I guess my key takeaway here is if you want performance, don't be scared of trying to get static dispatch, and do specialized code. So I'm going to talk a little bit about Quickwit as well. So yeah, Quickwit is the actual product of my company, and we are trying to build a cost-efficient log search engine. One first question that I get asked is, what's special about log search? So why not just distributed search? So focusing on log search, and actually log search, it's not really log search, it's append-only data search. So we focus just on immutable data, which means that we can also work on chat messages, for instance, or we can work on if you wanted to have if you have an immutable data set, like a snapshot of the web, like Command Crawl, you can use Quickwit as well. It's perfectly fine. The thing that we cannot do is modify a document that is already in the base. So yeah, we focus on this because it makes it possible for us to cut some corners and be more efficient. So we don't focusing on log search means that we don't care about search quality. People usually don't care about the order of the documents when they search for logs, or rather they're asking for an order that is more like, oh, I want them order by time, and they have a very specific idea of what kind of log should come back. So it's not like relevancy, it's much simpler. Second point is that it's very cost sensitive. So people who are searching terabytes of logs, they really care about how much it costs. It's not the case if you are, let's say, an e-commerce website that has a search engine generating billions of revenue. You're not really trying to optimize 10% away from your CPU because it's your money maker, and it's really not that much money you are spending on your server, so you just want the best result possible. It's immutable, and it's really helpful for a bunch of optimization. It's gigantic volumes and very few queries, which means that if you were to look into what your CPU is spent on your Elasticsearch cluster and you are indexing a lot of logs, usually very little CPU is spent on searching all of the stuff that you're doing is indexing, and we are very good at this. And yeah, also, usually you have, let's say that you are searching into application logs, you usually have different applications, or maybe you are a company, a SaaS company hosting logs, then maybe you have tenants. So you have this notion of when a search query is applied, you're actually searching into only one part of the index. So you are either multi-index or multi-tenant, and that's also something that we are very good at exploiting. So what makes Quickwit cost efficient? Tantivy first. Tantivy is fast, and it's really helpful for us, especially on the indexing side, which unfortunately I didn't discuss. And then the second thing, which is actually huge, is the fact that it's kind of our secret sauce. It's the thing that makes us very different. We make it possible to store your index on Amazon S3, so you don't have to do this thing where you have a bunch of server with very expensive SSD tied to the server, and you have to have your server to handle replication on their own. We put all of our data to Amazon S3, so we are paying only $25 per terabyte, and it's already replicated. It's super safe, so it's great. And so the difficulty is just to get good performance out of it, and we have a bunch of tricks to do that. So I called it segmented-based indexing because that's the way it's called in the Lucene world. But so, for instance, if we compare ourselves to a product like Elastic is doing document-based replication, which means when you are trying to index something, you push a document, the document is sent to all of your replicas, and the work of indexing, so like building the index, it happens on every single replica. So if you have 1+2 server doing this work, you are paying 3 times. So it's really a waste of money and a waste of resources. So here I meant segment-based replication, not indexing. Search and indexing are running on different hardware. It's not a well-known fact, and but it's very important to do that. I will explain why in in a later slide. Because of our architecture, we don't tie CPU to data. So all of the data is on Amazon S3, which means that on the search side, you just run a bunch of machines. You can switch it on. You can do whatever you want. And every single CPU is able to be used on every single piece of data, which is great because you never waste anything. It's not as if you have a farm of 100 CPUs and one of them is not working because it just does not have any data that is important for the query that you are running at this specific time. So we are able to utilize CPU more. And yeah, just because we are stateless, we can very easily let our users switch on their server at night or on the other side, just add a few servers for one day because they know that their traffic will be higher that day. So here I try to explain the contrast between our approach and the usual approach. So most of the distributed database that you work with are using a shared nothing architecture. The idea of shared nothing is you have a bunch of servers, you split your data into so-called shards, and you dispatch this piece of the data to the different servers. And you try to make sure that the shards are replicated so that if one server goes down, you don't lose your data. And here the CPU can only work on the data that is hosted on the same node. And that's kind of the point of what I was saying before. So yeah, I put two arrows. That's a very important part. So you want replica for two reasons, just to not lose the data. So having a replica is the normal way to deal with nodes being able to crash. And also that if you are running not a log search, but like an e-commerce search or something with a lot of traffic, adding replica is a normal way to deal with a higher throughput. And then if you have a dataset that is too large and you are doing too much computation when a query comes because maybe you have ranking or stuff like that, that's not useful in the case of Quickwit, but maybe you have too much data and in the case of Quickwit, then you do sharding, you split your data. So that's not what we do. So yeah, just to finish with shared nothing. Indexing works, as I said, by pushing a document to one replica, and the document itself is sent to another replica node, and it's indexed there independently. So you do the work twice, which is not great. So the benefit, it's still a good approach for many use cases, but not for log search. The benefit is that when you run a query, the CPU is working on data that is very close to itself. So you don't have to move it around, which is much more efficient than trying to move the data to the CPU. So one thing happens though, network is way faster nowadays. So it's very different than it used to be. It's faster and faster, so nowadays people are more and more turning to shared disk architecture, which is what we use. So in our case, what it looks like is we ingest data from a distributed queue. We consume this distributed queue from one or several indexing nodes, and we produce like files, actual files, that we upload to Amazon S3, and then we save the meta information on PostgreSQL, saying, oh, there is a new split, and from now on, searcher can search into this split. So very simple. We index every single document only once, and right after it has been indexed, we push that to Amazon S3, and it's replicated at this point. And then on the search path, the search starts by going into PostgreSQL and checking what are the splits that we should look into to perform our search. And usually, because it's logs, you have some extra information with the query. For instance, I'm looking into logs from the last week, and we are smart enough to put some metadata with the splits so that we can actually reduce the scope of our search to the splits that are within our metadata. That's usually called pruning. That's the kind of stuff. All of this architecture is very close to what you will see in a product like Snowflake, except that we do that for search. And then the search nodes, they are stateless, so they can search on any piece of the data. We can add server and switch off server and switch off literally everything, and it's fine. It's just getting its data from Amazon S3. Yeah, so I think there's a benefit that I already talked about. So we don't index several times. Storage is much cheaper, $25 per terabyte, and we can move stuff, switch off servers and switch on servers. So is everyone a software engineer here? Do we have SREs or DevOps? Oh, okay. So what's a good load average for a system? Yeah, exactly. That depends, right? It depends. Great answer. It's always.
Sorry to interrupt. Could you please repeat the question?
What is if you are looking into a server, what is a healthy system load average? So how much CPU, do you want your CPU to be used at 100% all of the time, or should it be a little bit less, or should it be more? I don't know. Usually you don't want more. It's a little bit of a difficult story, but if you are using your CPU at full capacity all of the time, then, and it's, for instance, an HTTP server, you should expect to have terrible tail latencies, and that's a very common problem that people have. So if you are at 90% all of the time, then just by random chance, sometimes you will have a bunch of requests that happen at the same time, and you will have a queue forming, and people will be waiting, and it's not great. That's yeah, you can look into queue theory. It's actually very simple. If you simulate it, it looks like this. So if you have a load factor that is of so here's the load factor, and we are looking here at the different curve for the different percentile. So if we look at the 90th percentile, so your server, what will be the tail latency at the 90th percentile, you see that it increases very fast as the load increases. And that's just a very, very natural phenomenon. But so if we come back to search, indexing, it's really a throughput game. You don't have a user behind you waiting for your request, right? So you just want to have the highest possible throughput, and you are perfectly happy to see your CPU at 100% or 90%. So that's a good thing. Search on the other side, it's absolutely the other way around. People are waiting for the search query to finish. So you want to have a load that is way lower. So by definition, you don't want to have these two things happen on the same hardware. And that's what we do in our architecture. You have nodes for search and nodes for indexing. At least you can configure it like this. That's all I have. I hope I wasn't too long. Do you have questions? Yes?
You precise that you do not support mutability in your system.
Yes.
But there is one type of mutability I was wondering if you support is, do you support erasing things over time? For instance, in a logging system, you would want your logs to stay for 10 years, but you want to rotate them. And I was wondering, since the way you're indexing things, you have an inverted index, how would you maintain this index whenever you need to remove regularly some blocks?
Yeah, I'm gonna repeat the question because I don't know if everyone heard it. So the question is, I said that we are working on immutable data, but when people are working with logs, usually they want to enforce some kind of retention policy. So for instance, they want to be able to remove logs that are older than 1 month or 1 year or whatever. So the way we build our index, we produce files that are called splits. There is a system that merges them together, but after a while, a split is considered mature, and we don't merge it anymore, and it will be, it comes with metadata, as I explained when I was talking about split pruning, that is saying, oh, this split only contains logs between this date and this date. So we also have a retention policy system that works pretty much like a cron job and says, okay, what are the splits that are outside of the retention policy? Let's suppress them. And that's just deleting files. So it's extremely cheap, much cheaper than trying to deal with tombstone and doing some kind of compact operation or stuff like that. We also have another case where people want to delete documents, and it's a little bit painful for us, but we handle it. It's stuff related with GDPR. So sometimes people want to be able to remove all of the information associated to one user. So that kind of request usually happens once a day or once a week, and you don't have to handle them right away. So what we do is that we have a system that does a bunch of those as a batch job. So it will queue them and then applies all of them on the different splits. So we handle that as well. That's the only immutability that we have. Other questions? Yes?
Are those C moves actually faster, or in your real production system, it boils down to SIMD, kind of some other parallel comparison?
Yeah, so the question is, are the C move faster? So you said, your question is in comparison to SIMD linear search or in comparison to branch code?
Maybe it's actually two questions. So C move, depending on the processor, can introduce hazards, so it's actually slower. But I really care about what's the production system look like? Does it use the same C move or something else?
So C move got a bad reputation because of the Pentium 4. It's actually very old data. So there is like some interesting threads on this. There is a historical thread, but C move on any recent processor tend to be actually very fast today. But then the question is, if you compare it with a branch, what is the branch very predictable or not? So if the branch is very predictable, then the C move will be a little bit slower. And if the branch is very hard to predict, like in the case of a binary search, which was our use case, then the C move code will be much, much faster. So in our case, it was way faster, yeah.
Right, and I'm asking the production system, do you do like a parallel compare in your SIMD code?
So yeah, we did a comparison. So no, it's not in parallel. It's not like an A/B test or something like that. It's a bench on actual data, but it's not in production.
Okay.
Yes.
You said that you support like multi-tenant, or you provide a multi-tenant service from your system. So do you have to take account like fairness or specifically, or is that kind of a best effort thing between your tenants?
Yeah, that's a good question. And I only have a bad answer. But so the question was, I talked about multi-tenancy, and do we have a system to do fairness, to have fairness among tenants, so that there is not one tenant that is using all of the CPU and the other tenants get slow queries and stuff like that? So no, we don't. Yeah, no, we don't do anything of that kind.
Does it work well in like practice?
No. No. The only thing that we do is that we have a system to So it's another part where we are very nice with people with a multi-tenant use case. Building a search index is something that is very expensive, but building 1,000 search index that are very small at the same time is something that is terribly hard, and every single index has a memory footprint that is quite important. And we kind of solve that problem, so that's what we are good at. And then we have this split pruning system that makes it nice. When you search into your data, you're not searching into the rest of the world, so it's efficient. But we don't have anything to isolate tenants in terms of resources.
Thanks.
Yes?
Does Tantivy, does it have any like P99 better performance than Lucene, based on not using the garbage collector and other figures like that?
Yeah, so I looked into that a little bit. Yes, yeah.
Yeah.
The long story short is, yes, the variance is much better than what you will see with Lucene. I don't show that kind of information in the benchmark. That's kind of voluntary because I use this benchmark myself to improve the performance of Tantivy. So it's not a benchmark that I use to boast. I use it to know where. Actually, there are queries where Lucene is faster than us, and that's very interesting for us because that means that there is something that you can dig into. And also, you've seen that there was this search engine called PISA that is faster than us as well, this academic search engine. So yeah, this search engine is mostly for search professionals. So Lucene people are looking at it as well, to look at the result and discuss. I don't care about like making fun of Java GC or stuff like that. But that's a good point though. So especially in distributed search, variance is really important, right? Because when you do a distributed computation, you are as slow as the slowest of the piece of your computation. So if you have a high variance, the latency that you experience is the max of the different stuff that you do, and so it really destroys your distribution way more than if it was flat. So it's much better. Yes?
You've shown some example of, for instance, for use case for logs, but have you tried the use case for metrics, which is very different because you don't need a lot of indexing, but you concentrate on data compression? Have you ever tried using the system for this?
Yes, so the question is, have we tried to use our system for metrics? So we do handle, we do have aggregation like Elastic. It's actually the same API. We haven't used it all that much, to be honest. Right now we are focusing mostly on logs and recently on tracing. And metrics will probably come at one point, but I'd love at one point to actually have a full-fledged time series, so go beyond what Elastic does on this. Yeah, so sorry, I don't have a great story to tell.
Great presentation. Thank you, Paul.
Thank you.
Just a couple of more things before you all go and chat. First of all, thank you for coming. This is my first time organizing the meetup. Raise your hand if it's also your first time at the Tokyo Rust meetup. Yeah, a lot of new people. That's great. So my plan is to have at least one meetup every month. And kind of the bottleneck is finding presenters, like people who want to talk about the project, something that they've learned. So if you feel like there's something you want to talk about, one of your projects or something that you think was difficult to learn about Rust, or some success story, whether you use it at work, please send me a message. And it's going to be a really big help for me. Or if you know someone else Also super helpful. All right, so that's all for today. Thank you for Paul for presenting. And the pizza has arrived. A little bit of a technical difficulty is they're smaller than we had expected. So we ordered more. More food is coming. Please don't worry. And let's go and enjoy the food and the drinks. Thank you.